All right, we're going to introduce one of the classics of organic chemistry. It's called the Diels-Alder cycloaddition. This reaction was developed in the 1950s, and in the 1960s, everybody who was anybody was doing Diels-Alder chemistry. It just took everybody by storm. So what is a Diels-Alder? The Diels-Alder is a reaction in which we take a diene mean a dialkyne, and a dienophile, something that's going to love to react with the diene, and these two things react to form a cyclohexene. So the mechanism of this, one pi bond attacks the dienophile from the diene. The dienophile returns the favor and attacks the diene. And then we break the second pi bond of the diene to make a new alkyne. This helps to number these carbons to keep track of where things are. And here's where the carbons end up in the product. So we get a cyclohexene product. This is a one-step reaction. There's no carbocation intermediate, no radical, no carbanion intermediate. So let's see some different examples of how these show up. You can have a regular diene, and your dienophile could be an alkyne. And if that's the case, when we do this reaction, we actually get a cyclohexene, which contains an extra alkene, because we had two pi bonds between carbons 5 and 6. And so we get an extra pi bond left over between 5 and 6, which we didn't see in this top structure. So you can have alkynes involved in the process. Another thing, you can have your diene. Your diene can contain a ring. So we make a new ring in our product. Now, since we already have an existing ring in our diene, now we're going to have two rings in our product. So if we did this reaction, double bond attacks back, and we move that double bond there, we are going to get, again, a cyclohexene. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. Now we haven't accounted for this CH2. That CH2 was attached to carbon 1 and carbon 4, and none of the arrows in our mechanism affected that. So it should still be a CH2 attached to that carbon 1 and carbon 4. So we have this multi-cyclic structure, and we're trying to represent it in 2 dimensions. And it turns out when people draw this, it's called a bicyclic structure. When people draw this, they draw it a little bit differently. They draw it kind of like this. So here's carbon 1, 2, 3, 4, 5, 6. And here's that extra CH2 that's bonded to 1 and 4. So this is probably a clearer way to represent the three-dimensionality of this bicyclic structure within the limits of having a two-dimensional writing surface. Now, so we've drawn these different Diels-Alder reactions going forward, taking the diene and dienophile, but it's also equally important to recognize that anytime you see a cyclohexene, you can potentially envision this as going backwards and having given you starting material. So this is more of a retrosynthetic type analysis. So what would be the diene and dienophile that would have reacted together to give you that cyclohexene? So we need to be able to think of these reactions as going forward, yes, but we also need to recognize that the product could be the cyclohexene, and we need to imagine what the diene and dienophile were.